Right there, I found it. Okay.
Is that serious?
No, it's yeah, it is, isn't it? Yeah. It is. Right, sure. Okay, we'll do a quiz tomorrow. We'll take a brief review. I forget how many minutes it is on Friday, right? But it's not the full 57 minutes like we have right now. So we'll do a quick review. When you guys are comfortable, we'll take the quiz, and then everybody should get A's, right? All right, homework tonight. Much more challenging than last night's. We did not, because we had the golf tournament.
Do you need graph paper for this?
Why would I set the one? Oh, that was for attendance. Yeah, I already did it. Will you need graph paper for this? The answer is yes, if you like graph paper to graph things. So these are going to be the weird shapes that you may or may not recognize from just their equations. Good? All right, here we go. Same class as yesterday, so we got everything through. We did equations with two variables, we did the intercepts, but we did not do symmetry. So symmetry is your first. Okay, I'm going to make this into a bigger deal than it actually is, right? But this is brand new. You have never seen symmetry, the test for symmetry and how you calculate symmetry. That's the new part. So I'm going to make a big deal like this is really challenging. It's not that challenging. It's just a little bit more challenging to remember and put it in practice. So when I say, boys, it's a pre-calc, I'm just saying like pre-calc happens and all of a sudden it's something brand new you haven't seen before. It's got procedures. You got to learn the procedures. Typically we'll have formulas involved. You got to memorize the formula or you got to have them written down type thing. And that's why it's a pre-calc lesson. You're doing something new, something a bit more challenging than normal. There are definitely some easy parts. There are a few parts that are slightly complicated, but it's all new. And that's what makes it really a pre-calc lesson. All right. And then, of course, it has some procedures to remember. So where did we leave off? Remember, the whole big idea is we're graphing an equation. We're taking an equation with two variables, typically a y and an x, right? And we're graphing it. And if you recognize the shape of it just from the equation itself, so in other words, if you know the shape, right, what it's supposed to look like, and if you can calculate the intercepts that we learned yesterday, and if you know it has symmetry, well, then you don't have to do this huge honking table of pain. You can do a reduced table of pain and apply symmetry to just a few points. And I'll show you, most of the time, we're only going to have 2 points, maybe 3 on a table of pain. Remember, if it's some weird shape you don't know what it is, you might have to do 50 points in order to find out what the shape is. So this is a much easier way of doing the table of pain for unrecognizable shapes, okay? We also need to know the end behavior. We'll talk about that as well, too. Then you can graph it all by hand without, now it says without a table of pain, without a complicated table of pain. We're going to do a reduced table of pain. Like I said, typically we're going to do 2 points in the table of pain. We're going to get 4 to 5 points for free because we're going to have this thing called symmetry and we're going to know the end behavior. Okay, so it won't be Danny doesn't have to put another staple through his finger. All right. So here we go. Box 1, write this down. So symmetry. Now you did symmetry way back in pre-algebra. You may or may not remember this. It's typically on most tests when you take just a standard test for your general knowledge. Symmetry is a geometric construction where one half of the shape is a complete mirror image of the second half. We didn't hand out sheets, did we? No. And I put them right here. You get a car. You get a car. You need a car. You get a car. You got a car. And just so you remember for all this stuff, if it's a nice one that already says y equals You can always graph it on your graphing calculator to see what it looks like, but typically some of these you're not going to be able to, it's not going to be the form of y equals. Still have to do this all by hand. That's what the procedure we're learning. All right, so symmetry is a geometric construction where one half of the shape is a mirror image of the second half. You kind of remember doing symmetry at some point?
Yeah.
Right? They usually would give you a shape and then ask you to,
draw it on the other side.
no, not really, but they would give you a shape and ask you, they would ask you if it's symmetrical, and if it was symmetrical, they would ask you to,
Draw, cut it in half.
right, find out where it folds over itself type thing. Where it folds over itself is called the line of symmetry. And that's that line that separates the two halves. And generally speaking, up and down, left and right, that sort of thing. Generally speaking. We'll find out today there's some more lines of symmetry. So we got the definition of symmetry and we got the definition of line of symmetry. All right, this is a weak example I'm going to show you, but it is what it is. So, hey, is that a symmetrical object right there?
Probably. Yeah.
If I straight down the middle. Now it's a biological specimen, so I mean your face, you think that your face is symmetrical, right? But really your left side and right side don't match up perfectly, but you get the idea. Okay. Are these symmetrical geometric shapes? Where's the line of symmetry? Right? For the one on the left, y-axis. For the one on the right, the x-axis. Yay, yay for us. All right, nothing challenging there. So it turns out that symmetry comes in three main flavors, right? And the three main flavors are box number what, 2? Yeah, box number 2. Flavor number 1. This is where it gets complicated. All right, look at the shape. Tell me something smart. Symmetrical about?
It looks pretty symmetrical.
About?
Oh, the x-axis.
The x-axis. Now tell me something smarter.
Oh.
If you are symmetrical about the x-axis, then
All
The x's
vertical lines.
have the same x value.
if you're symmetrical about the x-axis, the x values duplicate themselves. But what changes?
Why?
So it's kind of like that same thing we did yesterday for intercepts. If you're talking about the x-intercept, you let not the x equals 0, you let the y be 0. Same thing for x-axis symmetry. The x's stay the same. What is changing is the y, but how are the y's changing? Yeah, one's positive and one's negative, right? They're just offset if it's symmetrical about the x-axis. There's lots of type of symmetry. We're going to restrict ourselves to the x-axis and 2 other ones. You can imagine if this was shifted up 10 units, it would still be symmetrical, but it wouldn't be symmetrical about the x-axis. It would be symmetrical about, I don't know, the line, for instance, y equals 5 or something like that. Then it wouldn't be just positive, negative, but the distances between those 2 points would remain constant, if that makes sense. Okay, cool. So now I'm going to take that concept that you just told me correctly. We're going to write it with fancy words. Ready? All right, so there's the fancy words. So if you are symmetrical with respect to the x-axis, if for every point xy, that would be the points on the red, then the point x negative y is also on the graph. So any point you pick on the red, we'll call that xy, and that means then you get a 0.4 free on the blue just by taking the same x and putting a minus sign in front of the y value. Well, that's convenient. By the way, it also works the other way around. Pick any point on the blue, x negative y, make the y negative, so negative y would turn into a positive y. They write in terms of red to blue, but it could be blue to red. The math there would be exactly the same. Does that make sense? Okay. You wrap your head around that, we're halfway through the challenging part. Function, not a function. Function, not a function? That is not a function, right? There is an equation for that shape. You've never seen that shape before, but clearly not a function. All right, everybody good? We're going to do 3 of these. All right. We say this reflects over the x-axis. Okay, what do we got going on here? Okay, so tell me something smart. for every xy, if it's reflected with respect to the y-axis, then you get negative x comma y for free. And now we're going to write down all that stuff. You got it. And once again, that is a function right there. It's not all the equations that reflect over the y-axis are functions. This particular one is. Good. Okay. The last one, so we say reflect over the y-axis. The last one is the weird one, right? What's going on there? Okay, so how does that work? Reflect over the origin. Yeah, but what's going on there? When you say reflect over the origin, what's going on there? She's saying it's going diagonally, right?
Yeah.
Anybody else?
You would fold it and then fold it.
She says that if it's two reflections, this is reflect over the y and then reflect over the x. Turns out, or vice versa, turns out they're both right. It is reflected diagonally. We just choose not to say diagonally. Anybody can figure that one out? We're not going to say it's reflected diagonally, although that's true. We're going to say, how do you turn red into blue? Okay, hers correct, right? You flip it right, then flip it down. But there's another way, kind of the diagonal way. Okay, Mr. Artist. Can anybody see it? What if we rotated it 180 degrees? So if you take red and rotate it 100 degrees, that would accomplish the flip it diagonally. It also the same thing. And it's thought of as both ways. It's either thought of as a 180-degree turn, or it's thought of as two reflections, one over the x and one over the y. Okay. And then what you guys said at the start, what's really going on in terms of coordinates? Agreed, but what's going on in terms of coordinates? Yeah, you just put a negative in front of the x and the y this time, right? And that is called symmetric with respect to the origin. For every point on the red x, y, put a negative in front of each x and a negative in front of each y, and you get a point on the blue for free. So you got three of these now. It can be a little bit confusing. It has something to do with negatives. And one of them you apply to the x, one of them you apply to the y, and one of them you apply to both of them. You know, having it written on a resource card, you can never confuse them. But certainly, if you don't have it clear in your mind, you can screw this up pretty good. Everybody okay? All right, a couple slides for what you guys all already said. You said, hey, it's also reflect over the x and reflect over the y, right? Or vice versa. You reflect over the y and then over the x. That works as well too. Here's a weird thing. You ready? Pick any point on the red. I'm going to pick this point right here on the far left, or far right, sorry. That xy. And if you make the x negative and you make the y negative, you get this point right here. And the weird thing about it is, this is a claim, I'm not going to prove this, but this is a claim, is that if you connect those 2 points, the xy and the negative xy, it will always go through the origin. That is a very convenient thing, and that's only for this. It does make sense, but I'm saying it's a claim that it has to go through the origin. I have to prove that one. But that's the claim. Okay. All right. We won't use that today, but it is useful. All right. So those are two things. It's either referred to as a half rotation, 180-degree turn, or reflect over X, reflect over the Y. All right. So the first skill today is simply going to be, well, if it has symmetry, which one does it have? These are going to be called tests for symmetry. Guess how many they're going to be? There's going to be 3 because there's more than 3 symmetries, but the 3 that we're concentrating on, x-axis symmetry, y-axis symmetry, and origin symmetry. So there'll be 3 of them. All right. In other words, can you tell if the graph is symmetrical without graphing it? Right? Obviously, you plug it in your calculator, graph it, you can look at it, but we're going to be able to do this simply by looking at the equation itself. And there's 3 tests. Unfortunately, there's 3 tests. So this is the one that usually, and that's why homework's a bit more challenging, is because you got to do all 3 tests, right? All right, so there's going to be a test for the top one, a test for the middle one, a test for the bottom one, and they're not going to be the same. They're going to be 3 different tests, one for each one. If it could be true for all of them, it could be true for none of them, or it could be true for a couple of them, right? You might have x-axis symmetry and rotational symmetry, or origin symmetry, or you might not have any symmetry. All right, so we're going to write these down first, and then we'll explain what's going on, okay? So here are the 3 symmetry tests. So if you're testing for x-axis symmetry, you replace y with negative y, and if you see if the resulting equation is exactly what you started with. The one for y-axis, you replace x with negative x, and you see if the resulting equation is exactly the same as what you started with. And lastly, for origin, you replace x and y with their opposites and see if you get back to what you started with. If that's confusing, it won't be after we do some examples. And notice the verbiage here is exactly the same for each one. It's just that first phrase that replace something with something. That's the only thing that's changing here. The rest is exactly the same. We okay? Okay. So if you're lost, you won't be after we do an example. So how does it all work? They're going to give you an equation. You may or may not recognize what that shape is. All we're doing right now is we're testing for what kind of symmetry it has. Anybody recognize it?
Oh, it's an ellipse, isn't it?
It's an ellipse, right? It's an ellipse, right? And well, what you know about ellipse, does it have x-axis symmetry in ellipse? Right? Okay, if you flip it over the x-axis, you get the same shape. If you take an ellipse,
It depends on the.
now remember it's centered at 0, 0, right? So this one's centered at 0. So if you take an ellipse centered at 0, 0, and you flip it over the x-axis, you get the same shape. If you flip it over the y-axis, you get the same shape. You turn 180 degrees, you get the same shape. So we already know that from this. So it should pass all the symmetry tests, right? So sometimes you can, well, unfortunately for you, when we get to quiz and test day, I'm going to ask you those tests, and you still have to show me the test. All right. Okay, so the first one, and you can do them in any order. So we're going to do x-axis symmetry. And just like it was for intercepts, it's kind of the opposite. So we're going to take, for x-axis symmetry, we're going to take the y and make y negative and see if we get back to exactly. Now, think this through. I'm going to go back a few slides. So if we're testing for x-axis symmetry, notice, right, that what's changing is the y. But if you plug in y or negative y and solve for x, guess what happens? It's the same thing. So nothing should change if we throw for x-axis symmetry. If we throw in y or negative y, we should get exactly the same thing. And that's how this works. Okay. So here we go. To test for x-axis symmetry, I'm supposed to take y and make y negative. See what it did? Okay, what's negative y squared? What's negative y squared?
Y squared.
Y squared. So does that look like that?
Yeah.
That's how we know it has x-axis symmetry. So once again, the technique is you're plugging in a negative something, either a negative x or negative y or both, and seeing if you get back to the original equation. And if what you get looks exactly like what you started with, then you just proved it to be true or yes for that particular test for symmetry. Does that make sense? Okay. Yay, we confirmed what we already knew. It has x-axis symmetry. So yes for that one. All right, so for the next one, what do we do? Y-axis symmetry?
Make the x negative.
Now we're going to make the x negative and do the math. What's negative x squared? X squared. So does this look like that? Yes. Thank you, Wes. Therefore, it has x-axis symmetry. By the way, we already said it did. And then the last one, well, you can kind of figure this out, but don't always assume just because it works for the first one, works for the second one, it's going to work for the third one, right? In this case, it does. So if we replace x with negative x, y with negative y, simplify, hey, look, we got back to exactly the same thing, okay? So this one, we just confirmed what we already knew. This one has all three symmetries because it's an ellipse, centered at 0, 0. By the way, if it wasn't centered at 0, 0, right, it might not be true. Okay. So that's the easiest of the easiest one. We'll do a couple more of the more challenging ones. Ooh, look at that thing. Anybody recognize what that shape is?
That's
No, I don't recognize what it is, right? In pre-calculus, this is a very common thing where you get something that is completely, totally unrecognizable. Hey, could you, don't do it right now, but could you plug that into your calculator? You certainly could because it says y equals, right? It's a weird thing, right? It's really weird. Okay, so we're going to test it for symmetry. Okay, I always do these in order. You don't have to do them in order, but I'm going to do the x-axis symmetry. So Ben, what's the technique? I'm going to make the y negative. Does this look like that? Does blue look like blue? No. I mean, there's nothing, there's no trick. Hey, what if I multiply both sides by -1? Would it? No, because then the left side would be negative, and that didn't help us out. So it does not have x-axis symmetry. Okay, so that's a big fat no. Okay, what's the test, Jace, for y-axis symmetry?
Change the x to negative.
Change the x to negative x, and that's every x that's up there. Okay, simplify.
X squared, x squared.
Okay, so does blue look like the original blue?
Yeah.
Yeah, so this one has y-axis symmetry. So this one is reflected over the y-axis. And the last one, don't assume because this is no and this one's yes, that this one is obviously going to have to be no. We don't know until we actually do the work. So I replace negative x or x with negative x. I replace y with negative y. Clearly, the x's look good, but the y is still negative when I simplify, and that this blue doesn't look like the original blue, so therefore that's a no. Did anybody graph this?
Yeah.
Can you see that it has y-axis symmetry? Yeah. So if you flip that over the y-axis, then it would look exactly the same thing. All right. Okay, so the last skill we're going to do is we're going to put everything together what we did. Okay, so yesterday we graphed using intercepts and table of pain. And today we said, hey, maybe you can make your life a little bit easier if you know it's symmetrical. Now, I'm going to point out the obvious that even though the table of pain is going to be easier, we still have to do 3 tests. So in terms of time, this is still a long process. This isn't like a, hey, graph something in 3 minutes type thing. This is graph something in 3 to 5 minutes. Okay, so we're going to graph using the intercepts that we learned yesterday. We're going to do the test for symmetry. And once we understand it's symmetrical, then we can apply, we get 3 points. We're going to get 3 points. Because if it's symmetrical about the x-axis, then all we need to do is flip, make the y's opposite, and we get a point for free. All right. So anybody know the shape right off the top of your head? X cubed? You will. No. No. Okay. So that's good. We don't know what the shape is. Look, Ben's going to immediately grab his calculator and figure it out, right? But let's just say we didn't have that and we're doing this by hand. So, okay, step number 1, right? Step number 1 is let's find the intercepts. By the way, this doesn't have to be step 1. If you want to do tests for symmetry first, you could. But find the intercepts. Okay, from yesterday's class, Abby wasn't here. How do we find the x and the y intercepts?
So to find the x, you put the y0 in.
Okay,
The y
so to find the x-intercepts, we set y is equal to 0 and solve for y, therefore y is equal to 0. So it's 0, 0. The one that, was it this class that said this? Was that you, Kylie? No, that was the other class. That was the other Abby in the other class that said, hey, goes through 0, 0. Hey, this one goes through 0, 0, right? And you can prove that simply by doing the other one, right? So if this one's 0, 0, the other one's going to be 0, 0 because that's the intercept. Let y equal to 0. How do you get rid of a cubing?
Cube root the other side.
Cube root. What's cube root of 0? 0. So, well, we got exact. Duh. If this one was the intercept, so is that one because it's 0, 0. You understand the point? If it's 0, 0, you're both the x and the y intercept at the same time. Okay, cool. We found the intercepts. Okay. The next thing we're doing is we're going to test for symmetry. All right, in any order that you want, but I always do x-intercept first, not because it's easier, just I'm a creature of habit. We let y be negative and see if we get back to the same thing. Back to the same thing? Nope. Okay. Test for y-axis symmetry. Let x be negative. What's negative x cubed?
Negative x.
Negative x cubed, right? So is that a yes or a nope? That's a nope, right? And the last one, let them both be.
Yes.
Well, that's going to turn into negative x cubed. And yes,
Because you can get rid of it.
because we can multiply both sides now by -1. And look at that magic. Once again, just because the first two are nope doesn't mean the last one. This one actually has origin symmetry. So what does that mean? And what do you keep talking about free points? Okay. Once you figure out, is it symmetrical, right? It is about the origin, then we simply need to apply those rules for origin symmetry to get a free point. Meaning any point that we've already figured out, what's the rule for origin symmetry?
Just put two negatives in.
You put two negatives. Well, unfortunately for us, -0 is still 0, 0. So I didn't get a free point for this, but for any point I throw into a table of pain, I'm going to get a free point because it has origin symmetry. Same thing if it had x-axis symmetry or y-axis symmetry. You're going to get a free point for every single point you throw in. If it works out nice, you're going to find a different x and y intercept. Therefore, all that work you did for intercepts, which isn't that challenging, you get free points for it if it's symmetrical. All right, so we are still going to have to do a table of pain, but it's a reduced table of pain. So because it has origin symmetry, any point I find in my table of pain, I get a free one. Just a negative x, negative y. But we still have to do a table of pain. So when you have to do a table of pain, you're plugging in an x, make your life easy. Pick numbers that are easy to do, right? So when I do my table of pain, that's origin symmetry, give me some easy points.
-1.
Okay, watch this magic, right? He says pick 1. So let's throw in 1. What's 1 cubed? 1, 1. But we have origin symmetry, so that means for free we get -1, -1. So there's 2 points. Well, really, we only calculate 1. Give me another easy number. We could pick either -2 or 2, right? I'm probably always going to stick to positive ones. So pick 2. What's 2 cubed? 8. So that would be 2, 8. And for free we get -2, negative. You get the drill. Okay. So pick some easy points, right? 1, 1 or 1 gives us 1, 1. 2 gave us 2, 8. And then we have 0, 0, right? That we had for our intercepts. And then lastly, applying origin symmetry to these 3 points right here, except 0, 0 doesn't give us any love because we get -0, -0. We get -1, -1 for free, no math involved, and -2, -8. Does that make sense? How many points do I have now? And really, I only plugged in 2, right? So maybe the shape emerges, maybe you have to plug in more points, but I would always recommend after you do this original, I would say no more than 3 points should you calculate and get the rest for free. I'm going to take these 5 points and I'm going to graph them and see if the shape emerges. And this one's a little bit harder to see, but there's the shape. Okay. Now, did I put arrows on it? I did not. This should have arrows on it because it doesn't stop. Desmos never puts arrows on their graphs, right? Nor does your graphing calculator, right? But you know that this extends upwards and downwards, okay? That's the homework right there. That's the whole process, right? So I'm not saying that, even though I said, hey, this is a challenging lesson, it's not really that challenging, but it is a process and you got to understand the process. Okay. Clearly more challenging than anything you did in Algebra 1 or Algebra 2. Okay. Maybe well, maybe not. But most of pre-calc is going to be like that. It's going to be a process. It'll be new. You learn the process and maybe it sinks in, maybe it doesn't, but after some practice, it should sink in. All right, we're just going to do 2 more and call it a day. Yeah? Okay. Anybody recognize the shape? We talked about it yesterday. You guys brought it up.
Let's see.
Parabola facing which way?
Right.
Oh, yeah.
You sure?
Yeah.
Yeah,
it's
yeah.
the
Okay.
left.
Okay, you're correct. All right, but let's say you didn't know that, right? I don't know what it is. Both, by the way, both my pre-calc class figured that one out. We find the intercepts first. Okay, to find the x-intercept, we let y be 0, right? Find the y-intercept, we let x be 0. Yay! Square root of y squared is, technically it's plus or minus y, but the other side's 0. Plus or minus 0 is still 0, right? So once again, this one goes to the origin. So if that is the y-intercept, then the x-intercept will be exactly the same. Yay. The last one I do, we actually get to different. Okay, test for symmetry. Does this have x-axis symmetry?
It should be.
Well, what's the test? Oh, now Ben's changing his answer.
Yes.
To test for x-axis symmetry, let y be negative, and you should have seen the trick now. If it's squared, it's always going to turn back into what it started with. If it's cubed, you get the opposite, right? If it's anything to an even power, it's always going to turn back into itself, right? If it's an odd power, then you get the opposite. Okay. All right, so this one absolutely does have x-axis symmetry. Does it have y-axis symmetry?
No.
Absolutely not. And does it have origin symmetry?
No.
Nope. So this one has x-axis symmetry. Okay, so we're going to remember that. And remember, for x-axis symmetry, any point we find, right? What do we get for free?
Negative
A negative what?
y.
A negative y for free. Okay, so any point that we figure out, right, x, y, we get the opposite of y for free, which is convenient. I just wish that our intercepts were something other than 0, 0. Okay, so we got to do a table of pain. Hey, are you plugging in y's or x for table of pain? So look at what you're going to have to do. What do we have to do when we throw in an x? Look at the equation. We're going to take the square root. So when you pick numbers, don't pick 3, pick, I was trying to lead you on. Don't pick 3, don't pick 3, pick 9. Because the square root of 3 is some decimal, but the square root of 9 is 3. And you were right, we should also pick 4 and 1, right? Because those are things that we can take a square root of. So if I'm choosing 1, 4, 9. Those are going to be my points, right? So I think I only choose 1 and 4, but square root of 1 is 1. So we get 1, 1. Square root of 4 is 2, so we get 4, 2. I got my intercepts, 0, 0. And then Addie, what do I get for free? What do we get? So we get for free, we get, you got it. So all for free. And if we're lucky, 5 points the shape will emerge, right? If we're lucky. If not, pick some other numbers. Like I said, pick 9, pick 16, pick 25. But luckily for us, the shape emerged. There's my 5 points. Play connect the dots, put arrows, and you're done. So here's how you graph by hand weird stuff. Now, if it wasn't symmetrical, and that's possible, we'll do plenty of unsymmetrical, not today. Everything they give you today is going to be symmetrical in some form or fashion. And it makes it a whole lot easier. All right, last one. Have you ever graphed that before? No? No? Okay. You have, you just don't remember this one. All right. Ben's immediately going to graph it. All right. Spoil the story. Goes right to the last chapter of the book. All right. So let's say you don't recognize this one. Okay. Let's find the intercepts. Ooh, which one are we going to find first? X or Y intercept? Doesn't matter.
Why?
Y.
We find the Y intercept when we let be 0. What's the problem with that?
Multiply by 0.
So therefore it does not. So therefore it does not. What was the test? What doesn't exist?
Intercept.
The y-intercept, it has no y-intercept, right? Does not go to the y-axis. Okay, so what happens when we try to find the x-intercept? Well, to solve this, what would we have to do?
Multiply
By x, and now the x is dropped away. So guess what? It doesn't touch the x-axis. Here is this is a function, by the way. Here's a function, we'll just call it an equation right now. Here's an equation that has neither x nor y-intercepts. So we get nothing for free, right? By the way, multiply both sides by x, 0 does not equal 1. Is it symmetrical, though? Okay, so first one,
X.
No.
yes or no?
Yeah.
Second one?
Yeah.
Third one? Yes, so it has origin symmetry, right? Because if you multiply both sides by -1, you get back to the same equation. So it has origin symmetry. Therefore, any point we throw in the table of pain,
Negative.
-x, -y for free. We just got to pick some points now. Look at the equation. Understand that you have to throw those numbers in, pick and choose wisely. Jack, choose wisely.
Let's go 0 first.
We already did 0 for the,
You're right.
we got nothing.
Let's do 1.
Let's do 1, right? Therefore, you get the point. You get 1, 1, and for free we get -1, -1. Yay for us. All right. What's another smart number to throw? Okay, that's wrong. How come I never? This is the 4th year I've taught this class, and no one's caught that. And I didn't even catch it. I reviewed the slides last night. That should say y equals 1 over x, not
Yeah.
y equals or x equals y squared. That's just all I did was copy it from the previous one. All right, so those are not the droids you're looking for, but look, I did that part right. All right, so we get 1, 1, and for free we get -1, -1. All right, choose wisely again, Jack.
2.
Okay, is 2 a good choice? Is that okay?
Probably not.
Well, no, I'm saying is 2 a good choice? A bad choice would be like, oh, I don't know, it's a weird decimal, I can't even figure it out. Is 2 a good choice?
Pretty good.
It's a half. I mean, that's okay, right? So if we throw in 2, we get a half, or we get 2 comma a half, or 2 comma 0.5, if you want to write that. Okay, so now we have 2 points for free. Probably need more than 4 points. All right, think this through. Higher level math here.
4.
If he picks 4, we get 0.25. That's okay, but you got to graph 0.25. There are other numbers that will make our life easier. What's another number that would make our life easy? I'm not saying you had 4 is perfectly fine. 5 is perfectly fine, except that it's so small, you'd have to change the scale in order to graph it. Danny, come on, think of an easy number that I can throw in that makes my life easy. We already threw in 1. What happens when you do a copy dot flip?
It's negative.
What?
Oh,
It's
you good.
flipped.
It's flipped. Is there a number that if you flip would make your life easy?
Maybe.
What if I let x be a half? If you let x be a half, what would you get? I would get 2, right? We like 2, and by the way, it'd just be these numbers flipped around, right? So if I throw in a half, that would be 1 over a half. Do a copy dot flip, 1 times 2 over 1, which is 2. So how many points do I have now?
35.
Technically 6, because I got 3 for free. We could choose 4 and 1/4. 5 might be okay, but just remember we're graphing really, really tiny things. But we could do that, right? Point being is that I just want you to don't just the standard thing was -2 to +2, but those could be crummy numbers that make your life miserable. Pick numbers. So I got a total now of how many points with this?
Enough.
No, how many points do I have now? I got 6 points using the symmetry. Graph those 6, and there's the shape. And remember, we know it didn't touch the x or the y axis. Woo! Class dismissed. All right, we will talk about the quiz tomorrow before we take the quiz. Right? All right, Ish, hopefully that worked out for you.